Okay, so where we left off yesterday, I was showing you the trick, the first of a few tricks, good tricks. And remember, we were doing this. We weren't doing that. We already did that one. We were doing this, maybe. Yeah, this. Okay, we're going to look at the function f of x equals x to the n, so a power function. Okay? We're going to take the derivative of a power function. And we started off just, we start with our limit definition of a derivative, and then we're just going to get specific. And so we decided that if f of x is x to the n, then f of x plus h is just x plus h to the n, right? And so we came up with this expression that we've got to evaluate. Right? We've got to take this limit as h approaches 0. And it started to get a little messy. Right? We did a little Pascal's triangle trick, and we noticed a trend, right? We noticed that as we increase the power n, exponent n, in a binomial expansion, we saw a little trend. Now, this morning, I just threw something together that's a little more exacting. So here's actually the first few terms of the binomial expansion. Now let's take a look. Don't panic. It's no big deal. So it's the same stuff we had yesterday. Yeah. So what this says, take a look here. Limit of x plus h to the n minus x to the n over h. That's what we're trying to evaluate. If I take this x plus h to the n, this is what it becomes. At least the first few terms of it becomes that. It becomes x to the n plus n times x to the n minus 1. Remember, the powers of x are just going to step down progressively by 1 with each term, while the powers of h step up by 1. Times h to the 1 plus some other number, and we don't really care what the number is. It turns out the number is n times the quantity n plus 1 over 2. But big deal, we don't care. Just some number. Times x to the n minus 2 times h squared plus another even weirder coefficient times x to the n minus 3 times h cubed, etc. All the way on out to, there's n plus 1 of those terms. But n might be huge, right? So we don't know what n is. For whatever n is, this is the expansion, though, okay? And then minus our lonely little x to the n term at the end, right? And you guys saw the trend there. We were able to, first of all, horizontally cancel those x to the n terms, right? Which was nice. That meant that all the remaining terms had at least one factor of h in them, right? That we could factor out, okay? And so if we factor out that remaining, that power of h, what we're left with then is something, oh my gosh, I'm sorry. All right, so back to business here. So if we factor out that h then, and this is as far as we got, I think. You told me then that we're just going to end up with this n times x to the n minus 1 from the first term, and then that weird coefficient times x to the n minus 2 times h, plus an even weirder coefficient times x to the n minus 3 times h squared. The trend being that only this first term, which only had a single power of h, gets, after we factor the h out, no longer has an h, right? All the rest of them, because they started off with powers of h that were 2 or bigger, when I factor out the h, they're still going to have some h's attached to them, right? And so then when we cancel these h's vertically, and we take the limit that h goes to 0, right, all of these other terms, because they have h's in them to various powers, are going to go away, right? And so only that first term lives on, and that's our answer. There it is. Okay. How about that? So that's a pretty short little formula, right? That's one of our standard forms. So then we can summarize that. If f of x equals x to the n, then f prime of x equals n times x to the n minus 1. So describe what we do then. Like if I say I've got this function, y equals x to the 13th, what does y prime equal?
13x to the 12th.
Yeah, to the 12th, exactly. So we just bring the exponent down in front and multiply it by the coefficient, which is just 1 here, right? So we get 13 times x, and then I reduce the power by 1. That's it. Simple. A lot easier than what we were doing, isn't it? It's a pretty good trick. Okay, way, way shorter. Okay, so that's one of our good tricks in calculus, is that we can just do that. So try one of these. How about, just give you, what do you think happens with this one? How about if we try y equals 7x to the 10th? Try that. Try this. Try that. And try that. Try those three. See what you get. So what do you think about that first one? Yeah. So I'm going to bring the 10 down front. 10 times 7 equals 70. It's good. X to the, good, done. Perfect. How about that? What about this one?
225.
Ah, good. Okay, yeah, dividing by 2 is the same as multiplying by 1/2, right? So that's the very same thing. We can at least think about it this way as 1/2 x to the 5th. And so, whoops. So then y prime, if I multiply the 5 times the 1/2, there's my 5/2. X to the, okay, what about this guy down here?
12x to the -5.
Ah, good. It works. I'm going to follow the same rules. If I take the -4 out front, I'm going to get positive 12. X to the -4 minus 1 is -5. Okay. Now if I write that without a negative exponent, how would I write that? X to the -5 is equivalent to, say it again. What do we do with that? What's a negative exponent on top mean?
Well, you get a fraction.
Right?
Yeah.
Okay. Negative exponent on top is equivalent to positive exponent on the bottom, or vice versa. Negative exponent on the bottom is equivalent to positive exponent on top. Okay? All right. So how about this one then? What if we have y equals the square root of x? Ooh. Ah, there we go. Okay, there's the trick. How about that? That's the same thing as saying x to the 1/2. So then, if that's the case, what is y prime going to equal if we just follow our rule? 1/2 x to the -1/2, which if I write that with a positive exponent. Ah, okay, the negative on top, exponent on top, pushes it to the bottom. And so I'm left with just a 1 on the top. On the bottom, I've now got a 2x to the 1/2, which I could write as 1 over 2 times the square root of x if I want to write it with a radical, right? Okay. That's useful, and you can use it in situations that Maybe you didn't anticipate it first. Okay, let's do another one. So we got derivative of constant we did yesterday. We got power function. One more I want to do with this too. Yeah, here's the neatest. What about this guy? What if I have y equals x to the 1? Does the power rule work for, what's the derivative of x? Remember from when we talked about that earlier? What did we say that was?
0.
Derivative of constant was 0. 1, yeah. But see if this rule will is consistent with what we already know the answer to be. Yeah. It is, isn't it? If I take the 1 out front, I get 1x to the 0, and what's anything to the 0? 1. So it works. So it even works for that. So if we want to summarize, and let's maybe do that, where we are right now, here's what we know. We know the derivative with respect to x of a constant equals 0. We know the derivative with respect to x of x equals 1. And we know the derivative with respect to x of x, and these are different notation, right? Of x to the n, we just said is and x to the n minus 1. Now let's take a look at another one. How about the derivative with respect to x of sine x? Okay, let's try that one now. So if that's our function, see if we come up with a standard form, a trick for that one as well. We'll just start off with our limit form of the derivative. What's that going to become if Rf of x is sine x? What's that become for us? What's f of x plus h?
Oh, sine of x.
Minus over h. Okay, and from trig last year, do you remember what the sine of x plus h becomes? No, it's a little more complicated than that. Do you remember? It's the angle addition. Yeah, sine cosine plus sine cosine. Good. Okay, so that becomes, so this part right here then. So that part's going to become sine x cosine h plus, say sine 2x, this would be plus, yeah, plus sine h, cosine x, right? Remember that? Okay. Over, okay, then minus sine x over h as h approaches 0. Okay. Now what? And we might want to remind ourselves, I guess, remember we had, if we're doing a limit involving trig stuff, and if I evaluate this directly, I'm going to get 0 over 0, right? But if I'm doing a limit involving trig stuff, we might want to remind ourselves of those two special limits we had for trig. Remember we had, well, the easy one was what? Okay, good. The limit, I'm going to call it theta, sine theta over theta. As theta approaches 0 is 1. And then we also had limit of, remember the other one? Yeah, good. 1 minus cosine theta over theta. As theta approaches 0 was 0. Yeah, so those are our two special limits that we might want to see if we can somehow dredge those out of this. Say it again. Sine of h over h. Okay. Yeah, but now problem, you're right, we do. We see something there, don't we? There's something we've got. Is there a way?
Can you factor the sine out of the top?
Can we factor, well, we can't factor a sine out of the whole thing. But do we see some terms that have some stuff in common here? Well, the first and the last each have a sine x. Now that's a good idea. There's something to go with. How about if we group those two together, right? So let's reorganize this just a little bit. So we're going to get the sine x cosine h minus sine x. Put those together, right, over h. And then I can split this. If I've got a common denominator, I can split this into separate fractions, right? Everybody agree? I can split this into 3 separate fractions, and I'll just group those two together. Plus sine h over h times cosine x. How about? Okay. Now, the limit, the variable of the limit here is the h, isn't it? Right? The limit is only acting on the h. So what's the limit of cosine x as h approaches 0? Let me say that again. What's the limit of cosine x as h approaches 0? Are there any h's in that cosine x? So it's just cosine x, right? Because the limit, we're evaluating the limit as h approaches a value. So any other variable is unaffected, right? We're not worried about the other variables. The other variables, as far as the limit is concerned, are really constants, right? The limit is only acting on the h's. So this is going to be unaffected, right? But that looks pretty familiar, doesn't it? All right, so if I take the limit, I can break it up like so, kind of separate that out, right? In fact, let's go ahead and write this as 2 separate limits. Let's be a little more, I want to make that point more explicit. And what can I factor out here, by the way? Sine x. Okay, so I could pull the sine x out of each term, and because the sine x has no h's in it, I could even pull that out in front of the whole limit, because there are no h's that are being acted on, right? So it's a constant with respect to the limit. The fact that x is a variable is irrelevant as far as the limit is concerned. So we got sine x times the limit of cosine h minus 1 over h as h approaches 0, plus I can pull the cosine x out in front of this limit. I can split this into separate limits if I want to, right? Minus 1, yeah, there you go. Okay, so now these are limits that we know, aren't they? Now this one says the limit of 1 minus cosine theta over theta, but I could factor out a negative 1 here if I want to, right? So I could make that a negative 1 and make that, flip those around. Okay, let's do that. Is it going to make any difference anyway, though? Because what's the value of that limit? So what difference does it make, right? You could have just left it that way. So when we evaluate this, that's going to 0 anyway, so the whole product goes away. Okay, now what about this limit? That one goes to 1, right? So then we end up with 1 times cosine x. So what's our answer? Cosine x. We got an answer. Right? So we can go back here and we can fill in the blank on this guy. It's not a question mark anymore. We know what it is. It's cosine x. The derivative with respect to x of sine x is cosine x. Yes. Good question. It went away because the limit went to 0. So negative sine x times 0 is 0. Yes, sir.
So do that by graphing it, like if you look at
Yeah, you could. I mean, you could.
Because the slope is like, it starts as 1, and so you start at 1, and the graph of cosine starts at 1.
Yeah, you could. I wish I had. Man, I wish I had my old. With Windows 7, this old graphing tool I had that I used last year doesn't work anymore. But you can actually take a function and then show its graph, and that's what you see. If I graph a sine function, and then I graph its derivative, you can just see, yeah, it's a cosine function, and you can see that they're compatible by playing that game we did yesterday, by looking at the derivative function as the slope of the original function. You know, if you think about the slope sensor on the end, you can see it. I mean, it just works out, so it just works perfectly. Yeah. Now, if we continue on, I won't go through this one. I think it's good enough to see one of those because the math is almost identical. But if I were to, while we're at it, oops, went the wrong way. I can add another standard form while we're at it. The derivative with respect to x of cosine x, it turns out, is negative sine x. So now we've got a bunch of them we can mess with that we don't have to do any limit stuff with anymore. We just know those standard forms. Okay. All right, so let's apply this to a little kinematics. Do some fun stuff here. Okay, let's say okay, remember yesterday I told you that if we define some kinematic functions, let's say position is given by S of t, velocity is v of t, and acceleration is a of t, then the kinematic quantities are related by calculus. The velocity is the derivative of acceleration, and position is the derivative, or hang on a second. Yeah, velocity is the derivative of position, sorry. And acceleration is the derivative of velocity, right? And so if I were to do something like this, let's say we've got a position function here. Let's say for on Earth, what you guys tell me? What's the equation for the position of a function that's accelerated? Do you remember what the position function is? Have you guys done this? Do you know the equation of motion for position? Yeah, well, I mean, you might call it, maybe you call it displacement. Okay, so you'd leave out that. Okay, so what would you say this is then? If I call that, is that how you write displacement?
Delta D.
D? Oh, that's bad. Okay, I'm gonna call it delta S. Well, I mean, it's just a textbook that uses that. I mean, there are different textbooks for different things, but D, you see why D is the problem? Because when you start doing calculus, D is the notation for a derivative, and the derivatives get wrapped up in the kinematics. So we'll call it delta S. What's displacement? You call that delta T? Time. Okay. Okay. Good. Okay. And the reason. Okay. Now think of what delta S is. Delta S is the change in position. Really, is what it is, right? We would define delta S is final position minus initial position. That's all it is, right? And so if we really want to write this, I understand why people write this in terms of displacement, because that's oftentimes what you're interested in. But if you want to write it as an equation of motion, what you really want to do is you want to write it in calculus sense. So when you move on and start doing calculus-based physics, you'll want to write that as S of t, because t is the independent variable, right? And then instead of that delta S being an S minus S naught equals, we'll just add the S naught to the other side, right? So we'll get initial position plus initial velocity times time plus 1/2 AT squared, right? Okay. Now, do you remember what the equation for velocity was? Well, okay, that's average velocity, sure. And you guys, and when I say velocity, you guys are dealing with averages because you're not doing calculus-based physics. So you're making some assumptions here when you're doing calculus, doing physics, which are that the acceleration is constant, right? Acceleration times time. Okay, good. Plus, and so the initial velocity plus acceleration times time, right? Because whatever you're starting with, and that's going to be the change in velocity. So you're making some important assumptions. You're assuming that the acceleration is constant. And so you're always kind of dealing with averages. And you can deal with maybe the initial and the final, but finding the values in between is a little difficult when you're doing algebra-based stuff. Now, when you add calculus into the fold, it just like turns that exponentially more powerful, because then you can deal with the functions and the way they relate to each other as instantaneous quantities or functions instead of averages. And that makes it much, because in real life, how often is the acceleration constant? It's never almost, In free fall, something is, you might treat it as being constant, but it's not, because as soon as it starts to move, the air resistance is a complicated function of speed. As it picks up speed, the air resistance increases, and so it's really only if you're in absolute vacuum is it really truly. You see what I'm getting at? If you hit a baseball with a bat, you can sort of treat it like the force is constant, and that's. Physics is basically just, your job in physics is to make assumptions. You're never going to be 100% right, but make good assumptions and make it as easy as you can. If you want to be a little more accurate with that, though, if you look at the force profile, at the impulse, when you hit a ball with a bat, it really looks like this. If this is force, and this is time, it kind of does something weird like this, where it kind of shakes around and does something like that. The ball, literally, if you look at it, it forms. The baseball becomes almost flat when you hit it. And while it's compressing, the force is increasing, and it springs off the bat. But it's not at all. It's not constant at all. And so these assumptions you make, although they're fine, they're better than nothing. And it's where you start. Later on, when you start to look at it as a calculus-based science, the mathematics, it just gets so much more precise. And that's what you got to look forward to. So stick with it, I guess is what I'm saying. Okay, so in case you forgot what the velocity function was, let's derive it. You'll never have to remember it again, because now, as long as you can remember the starting place, velocity is just the derivative of position, right? So let's just differentiate this thing term by term using our new trick, right? We can take the derivatives. When we take the derivatives of a polynomial, we can just differentiate each term separately, right? That makes it really slick. So the derivative of the first term, which is a constant, right? The initial position is just a number. That's a constant. Is going to be what? 0. The derivative of the second term, I've got some constant times t to the 1. So what's the derivative of t? Now, instead of x's, we're using t's now. No, 1, isn't it, right? As we said, we have our little list. Where's my list? Right there, right? Okay. Now it's a t instead of an x. And so we end up with v naught times 1 plus 1/2 a. Now we're assuming here, right? Now if we're talking about constant acceleration, which we said we were, right? Then 1/2 a is constant times the derivative of t squared. If I bring that 2 down, what do I get? Well, the a is going to stay there, but the 2 times the 1/2 becomes a 1. Then I get a t to the 1. There it is. Right, so there's your velocity function, right? And if I calculate acceleration, what should it be? I mean, we said it was constant, right? So it should just be a. Is it? Derivative of v naught is, that's a constant, initial velocity, so that goes away. And then the derivative of a times t, just a, because the derivative of a is a constant and the derivative of t is 1, right? How about that? So it works out. Okay. Now what gets really cool is when we can say, if I know the position function of an object in detail, if I can go the other way, if I can do the opposite of derivatives, I could start at position and work my way up to acceleration. I mean, from scratch, without, does that make sense? No, I'm sorry, I said that backwards. If I started with acceleration, I could work my way down to position. So all I'd have to do is if I could just find out what I could do some measurements on some weird planet and find out what the constant acceleration of gravity is, for example, or if it were even non-constant, if it were some weird force field acting on it, so acceleration were some complicated function of time or distance, I could work backwards then and calculate using the opposite of what we're doing now, and it's actually called anti-differentiation. I could work backwards and find out what the position function would be. So you could predict the position of an object as a function of time. That's what's really good, okay? So we'll get there. That's later on. All right, so let's just, you're going to have to live with this because physics is my first love here, so you're going to have to live with doing a little physics every now and then. Let's try something. I'm going to start off with, to get everybody kind of on track with this, let's start off with some non-calculus physics, just using the equations of motion. So let's say we know here that, well, we're going to use MKS, so meters, kilograms, seconds, MKS units. So we know then that our equation of motion is, let's see, we'll say S of t equals S naught plus V naught t plus, what's the acceleration of gravity? 9.8. It's actually negative 9.8, right? So I got to make this a negative. Plus negative 9.1 half times negative 9.8 is going to give me, why is it negative? Because it goes down, and we say that the standard y direction would be positive is up, right? So minus 1 half of 9.8 is 4.9 t squared, okay? So let's do this one. Let's say we throw a ball up in the air. At a velocity of 25 meters per second. I want to know, how high does it go? How long does it take to get back to you? Okay, something like that, and maybe how about how fast is it going when you catch it? Okay. So this is non-calculus stuff, just algebra-based physics stuff. So what are we gonna do? If we want to know how high does it go, what can we do? And by the way, if we know this, we also know the other equations of motion, right? We said that we could differentiate this. I guess there is a little bit of calculus. If I take the derivative of that to find velocity, what do I get? In terms of constant, so its derivative is 0, right? So that derivative of v naught, a constant times t is just the constant. So initial velocity minus, yeah, okay, and bring the 2 times 4.9, 9.8 t, okay? Okay, so if I want to know how high does it go, there's a couple strategies I could use. What do you think? We're just going to ask the math guy, maybe the physics guys. They're going to tell us here. Well, how are we going to ask them? We're going to set up an equation. What's gonna happen if, now think about this, what's happening at the top of that throw? Couple-
Reaches 0.
Okay, what reaches 0?
Final.
Okay, so one hallmark of that particular instant is gonna be that that's when the velocity goes to 0. Throw it up, the velocity is positive, it's getting smaller, 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 gets to the top, it's 0, and now it starts to get negative when it's coming down, right? Make sense?
Yeah.
Because we say up is positive, down is negative, right? So that's one thing that happens. What if I were to look at that position function, okay? And we could plug in the numbers. What is the initial, say the initial position is 0, right? The initial velocity is positive 25. So we could plug numbers in for those. If I were to graph that quadratic function for position, what would it look like? It's predicting position. It's going to be a parabola, isn't it? And does that make sense?
Yes.
It's going to be a parabola, and the biggest value it's going to give me for position, the highest it's going to get, is going to be at the peak. So that's another way I could look at this, right? I could look at that function. Got really two options here. I could either say, I've got my velocity function, and let's be specific. That's going to be, oh, darn it.